Hi guys, I just wanted to take a quick look at this question on the Solow model, not because it's a particularly interesting question in and of itself, but I want to use it to look at some of the different solution methods. So in the last videos, I showed you how to derive an analytical solution to the Solow model, and I'm going to show you how to compute it numerically as well. And using this question, I'm going to compare those different solutions. So the question is very simple. The economy starts on the balanced growth path, and then over some interval t lower bar to t upper bar, the growth rate increases to g prime, and then at t upper bar goes back to g. Okay, let's look at how we might solve this on a computer. This is a program that I've written to do this, and the first step in any numerical model is to just declare all your parameters. So in this model we have alpha, capital intensity of production, delta, depreciation rate, savings rate, the two growth rates that are denoted by G1 and G2, and population growth, N. And my T lower bar and T upper bar are going to be 10 and 40. And I'm going to calculate the capital stock and the output per worker at every point from T equals 0 to T equals capital T here, AT. So this program contains three different ways to solve it. If I skip down to them here. So the first one is just the analytical solution. Plugging the appropriate variables and the appropriate parameter values into the formula that we derived in the previous video. The second one and the third one are both numerical methods. The second one uses a very simple numerical method for solving ordinary differential equations called Euler's method, where you basically treat the time derivative as a finite difference. So instead of being the change of k, for example, over an incrementally small period of time, it's over a small but finite period of time. And rearranging, you can get that kt plus 1 is equal to kt plus the increment of time dt times what's on the right hand side of the ODE. The third solution method is essentially the same, but using MATLAB's inbuilt ODE solver, which uses a more sophisticated method for solving ODEs than Euler's method. Okay, so let me just talk through the first one. So in this section, I'm declaring a series of functions. K over AL star is just the capital per effective worker on the balanced growth path or in the steady state. And because we want G to change here, we want to allow G to change, I'm going to make this a function of G. But otherwise, this is just the standard formula for the steady state for capital per effective worker. A and L are pretty self-explanatory here, I think. And then line 41 and 42 is the expression we derived in the previous video for capital per effective worker at every point in time. So this is a function of T over here. And you can see here we have the capital output ratio in the steady state. And over here, we have the difference between capital per effective worker at the starting point, K0, and the steady state value. And over time, so when T equals 0, this thing is equal to 1. These two things cancel. So capital per effective worker is just going to be given by the initial condition, as you would expect. But as T increases, capital per effective worker is going to tend to the steady state value. And over here, I'm just declaring some functions that are the right-hand side of the ODE. So this is just savings, S times output, and then effective depreciation here, for the two different levels of growth. In this section, I'm declaring some helpful series. So the first three lines are just the series for total factor productivity. So TLB, this is the TFP at T lower bar. So when the G initially changes. Then at T lower bar, the growth rate increases. So this point is, so we need to account for the fact that after T lower bar and between T lower bar and T upper bar, the growth rate of TFP is higher. So this gives TFP at the end of that interval at T upper bar. And then this line is just stitching those three series for TFP together. Line 52 to 54 is just the capital per effective worker on the balanced growth path. So, of course, in the first interval between T0 and T lower bar, the capital per effective worker on the balanced growth path is going to be given by plugging the initial growth rate into our formula for capital per effective worker on the steady state. In the middle section, in the middle interval between T lower bar and T upper bar, we plug in the higher growth rate, and then again, after T upper bar, we plug in the lower growth rate again. And then output per worker is just capital per effective worker. It should be raised to the power of alpha here. And let me get rid of that here because this technically should be capital per effective worker. So what we have here now is truly capital per effective worker, and this is output per worker on the balanced growth path. Now, solution method 1, the analytical solution. So this is stitching together 3 time series, and in all 3 time series I'm just plugging in the appropriate values into our formula that I wrote above here, the capital per effective worker. I'm plugging in the grid for time, so this is a grid for time between T0 and T lower bar. I'm plugging in the growth rate that applies at that time, in that time interval, and I'm plugging in the initial condition. At the start of time is just going to be KAL0, which is just capital per effective worker at time 0. In the second time interval, I'm plugging in this point, which is just the T lower bar to T upper bar. I'm plugging in the higher growth rate, and I'm plugging in this new initial condition, which is just the endpoint of this time series. Okay, so I'm plugging in the level of capital per effective worker that I have just found from this at the end of the first time interval, so at T lower bar. And in the third time series here, I'm doing the exact same thing. I'm plugging in the time indices for T upper bar till cap T. I'm plugging in the lower growth rate again because we're now in the lower growth region. And I'm plugging in this complicated expression here, which is actually just the initial condition at T upper bar, or in other words, it's the end point of this time series. And then all I'm doing here is raising this time series to the power of alpha to get output, and then output per effective worker, and then multiplying it by my time series for TFP. So that's the analytical solution method. I can also use Euler's method, which is the simplest way, probably, to solve an ODE. I just start with capital per effective worker in the initial point, the initial condition, which remember is on the balanced growth path. And then I just iterate from T0 to T upper bar on this expression here. So this is saying that my capital per effective worker in the next point in time is going to be equal to its current value plus the time increment dt times this expression here, which is just the right-hand side of the Euler equation. So just it's perhaps easier to write this down. So my ODE for capital per effective worker, remember, looks like this. And all I'm doing in Euler's method is remember the definition k tilde dot is just defined as the limit as delta t of t plus delta t tilde minus t tilde divided by delta t. That's just the definition of a derivative. And I'm saying it's approximately equal to kt plus delta t minus kt divided by delta t. So not a limit anymore, but just a finite difference, delta t. And just rearranging this, of course, we get kt plus delta t tilde is equal to kt tilde plus delta t times this expression on the right hand side, s kt tilde to the alpha minus delta plus g plus n kt tilde. So everything on the right hand side is known here. Obviously delta g, n, s, these are all just parameters, but starting from my initial condition k tilde 0 given, I can then find k delta t tilde and then k 2 delta t, etc. for any t. Back to MATLAB. So this is exactly what solution method 2 does. The only complication here is that because I have 3 different time intervals, I need to have these 3 separate iterations. And finally, solution method 3 is just using MATLAB's inbuilt ODE solver. So this will use more sophisticated techniques than Euler's method, Runge-Kutta methods, for example. We don't need to know what they are. But that should give you a more accurate solution. And these inbuilt ODE solvers, there's a bit of a trick to them. So ODE 45 is the main ODE solver for MATLAB. So that's the default one I recommend you use. ODE 1 is my function that I defined up here, which is again just the right hand side of the Euler equation. This is not, of course, a function of t directly, but I need this t here for MATLAB. So you can kind of ignore that, but it's just for MATLAB's sake. The second argument of this ODE 45 function is the 2 boundaries for the time index. So t0 is the starting time, and TLB is the end time for this first part of the ODE. And there's the initial condition. The second line here, line 83, is going to solve capital per effective worker at any point between t lower bar and t upper bar. So you can see I'm now using ODE2, which has the higher growth rate. I'm now plugging in time indices between t lower bar and t upper bar, and I'm plugging in an initial condition, which is just the endpoint of this series for capital per effective worker that I've just found. And likewise for series 3 in line 84. In line 87, I'm just stitching these 3 time series together, and line 89 gives me output per worker. Okay, So let's run this now. Okay, I've now run the program, which has given me all three solutions in these three boxes here, and you can see they're all pretty much identical. The blue here is the transition path for output per worker. The black dashed line is output per worker on the balanced growth path. So at t lower bar here, which is just when t equals 10, you can see because the long run growth rate of TFP increases from G to G prime, output per worker on the balanced growth path drops immediately, but it grows at a faster rate subsequently. And then at T upper bar, which is T equals 40, when G reverts back to its original level, the balanced growth path for output per worker jumps up again and then grows at the original slower rate. And the blue here is the transition path. This is the analytical solution. This is using Euler's method. And this is using MATLAB's inbuilt ODE solver. And they all look very similar. And this final quadrant here is just the numerical approximation error. So the blue line is the difference between this blue line here, the solution as found using Euler's method, and the solution found using the analytical solution. So you can see we're on the order of 10 to the minus 5 here, so a very small approximation error. If I wanted to get an even smaller one, I could just use an even smaller time increment. So I used dt equal to 0.1. If I chose dt equal to 0.01, it would take a little longer to solve, but it would give me an even smaller approximation error. And the red oscillating thing here, and this is just the approximation error using MATLAB's ODE 45. Don't worry so much about these oscillations. The key point is that on average, this is going to be a slightly more accurate than the blue method. So Euler's method is very simple, but it's quite inaccurate unless your step size is extremely small, unless your dt is extremely small. Whereas MATLAB's inbuilt ODE solver will give you a slightly better, more accurate approximation. Okay, that's it. Thanks very much.